The tonicity of the external environment will affect osmosis. And osmosis, the direction of osmosis, has everything to do with water potential, which ultimately comes back to solute concentration. So when we're looking at this, osmosis is the diffusion of water, and water is going to travel towards high solute. So when we look at this demonstration, we're going to imagine this red line is a barrier to solute, which is the green dots, the substances suspended in water, but water can cross the red barrier. So in this case, the solute wants to be balanced on either side of the membrane. Since it can't go down, water is going to travel towards the solute to try and dilute this area and concentrate this area. So although the green dots can't go across, if water can go across, ultimately you would expect this to increase in the amount of water and become more diluted, and this area would become more concentrated. So again, water travels towards high solute concentration. When we look at this, we can talk about high solute concentration, but there's some more terminology. High solute concentration means the same as high osmolarity, which would equate to low water potential. The opposite of low water potential would be high water potential, which is synonymous with low solute concentration and low osmolarity. And again, water is going to travel from high water potential towards low water potential, from low solute to high solute, and low osmolarity to high osmolarity. On the AP formula sheet, we have all this stuff about water potential and solute potential. And you have all these constants, and you have temperature, and you have all this kind of stuff. So I'm going to try and get down to what's actually important here. So we have water potential, which is represented with this symbol. Solute potential has an S here, and this is the formula for solute potential. And within this formula, what's most important is the C, which stands for the molar concentration or the solute concentration. So as a demo here, if we have two substances and they're separated by a semi-permeable membrane, solute won't get across, but water can. On this side, we would have a high solute concentration, and this would be a low solute concentration. This side with the high molar concentration or high solute concentration would have a big C. This one would be a small c. A big molar concentration is going to equate to a small solute potential. So when we look at this, again, there you see this negative here. So the greater the molar concentration, the smaller the overall number here. So a big C is a small solute potential. And in this case, again, if this were pure distilled water, there would be 0 for molar concentration, and 0 would erase this whole formula and give you the greatest solute potential possible, which would be 0. So as we keep going here, again, a small molar concentration will equate to a large solute potential. When we look at this formula with solute potential and water potential, a large solute potential will give us a large water potential, and a small solute potential will give us a small water potential. And again, when we start thinking about osmosis, water is going to travel from high water potential to low water potential, which again, when we come back to this visual representation, we are just thinking that water is going to travel towards high solute concentration. So when we start talking about tonicity, we have a cell and we have the surrounding environment. If it is isotonic, it has the same or equal solute on either side of the membrane. So therefore, which way does water travel? If we're thinking about animal cells or red blood cells here, the water would go in and out at the same rate, and you would expect to have the same looking cells before and after it's put in the solution. Again, plant cells, same amount water in and out. That's isotonic. When we think about hypertonic, if someone is hyper, we often talk about them having high energy. So hypertonic solutions have more solute than across the membrane. So if there's more solute here, which way is water going to travel? And it's going to go out of the cell, which would cause the animal cells to shrivel up. And in plant cells, it would pull the cell membrane away from the cell wall, and the plant would become flaccid. Hypotonic, hypo is less. So in this case, the hypotonic solution has less solute. And again, the solute's not crossing the membrane, so which way is the water going to go? In animal cells, you would expect the water to rush into the cell, which can be very dangerous because we don't have cell walls, and we could cause the cells to lyse or burst. When it comes to plants, that just adds turgor pressure, where the membrane gets pushed tight against the cell wall because that large central vacuole gets packed full of water. When it comes down to plants, that's the reason why they wilt, because they have lost water. When you add water to the environment, we end up having it be turgid and they look fresh. So again, hypo, hyper, isotonic has to do with the external environment, and that will lead to osmosis, and water potential is determined by solute concentration and will determine the direction of water movement.